So going back just to real quick recap density curves that you learned in chapter 2. Of course, I'm sure you remember that the area underneath them was 1. The uniform density curve, of course, was flat across the top, but here I could prove again that the area underneath it is still equal to 1. The segmented density curve, most of you hated. Here's an example. Remember, I had to divide this up into shapes that I knew, so here I would be dividing it up into a rectangle and a triangle. Those are my calculations to show that equals 1. And of course, normal density curves are also probability distributions, as evidenced by the fact that I went and looked at a table to look up the probability, or the percentage, same thing, or the area. But since it was less than 1, that kind of turns it into a probability. Okay, so probably if you check the area underneath that, it doesn't equal 1 because I just made it up. But I want to make the point that if we were doing a continuous random variable and we were looking at probability that x is greater than 3, remember when we did this, it didn't make any difference if I said greater than or equal to, because of the fact that the probability, and I tricked you on this a few times, the probability at 3 is 0 because I have no thickness at a particular number. But when I look at discrete random variables, and we're going to start looking at their graphs, they're going to end up being bar graphs, and each one is going to represent a single number. So this is the 3s, this is the 2s, this is the 1s, and I could put some probabilities on here. But now there is a difference between greater than 3 and greater than or equal to, because if I do greater than 3, I just want this bar. If I do greater than or equal to 3, then I want both bars. So these are not the same. Some other things to kind of jog your memory that are going to come back up in these later chapters is the difference between mu and x bar. Remember, mu is the population mean, while x bar is the sample mean. We'll become more picky about that as we roll along second semester. And p represents the population proportion, while p hat, I don't know that we've actually looked at p hat. Ooh, what happened to his little hat? It was there. It should still be there. Bummer. Put that little hat over him. That represents the sample proportion. This is just throwing some vocab and symbols at you. And both of these are parameters because they come from the population. And both of these are statistics because they come from the sample. And one way to help you remember that is sample, sample, statistic, versus over here, population, population, parameter. And then both p hat, again, I don't know what happened to the little hat, it was there. Both p hat and x bar work similarly on normal distribution p hats, and x bars both find, I forgot what went there, I remember now, both, and that we find a z-score for both of them to calculate a probability. We're going to do a lot more of that second semester.